Galaxies a billion light-years apart can point the same way. The immediate takeaway is simple. The universe keeps fingerprints across scales. These patterns are not copies, they are correlations across distance. Gravity remembers tiny ripples from the beginning and organizes matter, so faraway regions can still dance to the same beat. Today, we will track that beat through deep space. We will watch it in light, matter, motion, and magnetism. Each piece shows how order survives, even as everything expands. No suspense here, the core idea lands immediately. Early universe physics set the rhythm, and gravity kept the time. By the end, that rhythm will feel obvious and strangely beautiful. Picture the infant universe, glowing plasma stretching in every direction. Tiny pressure waves rang through it, like sound in a bell. A cosmic pattern is simply a statistical echo linking far regions. It matters because those echoes let us read the universe's origin. Inflation stretched quantum jitters to astronomical sizes, freezing their relative strengths. Gravity then amplified overdense spots, while underdense zones thinned out. Photons scattered off electrons, carrying imprints of those rising and falling waves. When atoms formed, light decoupled, and the imprint streamed across space. We still see that light today as the microwave background. Its temperature varies by tens of microkelvin across the whole sky. Spots separated by certain angles prefer to be similar or opposite. That preference is the correlation, not a literal repeating wallpaper. Planck mapped it with exquisite detail, confirming the spectrum of ripples. The map's statistics match near-scale invariance, slightly tilted from perfect. That tilt says larger waves had a little more initial power. Galaxies later formed where those waves stacked, building a familiar pattern. So the CMB is the seed ledger, written very early, and the late universe is the harvest, grown from that ledger. The linkage persists because physics is consistent across space and time. Where the start was slightly high, gravity made it higher. Where the start was slightly low, expansion kept it emptier. Even after billions of years, the ordering survives in statistics. Example in real terms, neighboring sky patches share subtle temperature trends. On 40-degree scales, that trend stands out in correlation curves. Net result, the background light proves patterns can bridge immense distances. Shift to matter, the hidden scaffold built mostly from dark matter. Here, pattern means clustered pairs are likelier than random at some separations. Caring about this tells us how gravity grew structure from seeds. Dark matter interacts mainly through gravity, so it collapses quietly and early. Small halos form first, then merge into bigger halos, creating nested hierarchies. Filaments funnel material into nodes, while sheets peel away from voids. This process defines a correlation function, the extra likelihood of neighbors. At a few megaparsecs, pairs are several times more common. At tens of megaparsecs, the preference softens, yet still persists. Beyond that, it fades toward uniformity as expansion stretches space. Simulations show this clearly, painting streams, shells, and tidal bridges. Galaxies inherit their homes, orbiting inside halos that remember past flows. Gas feels shocks and cooling, but the skeleton remains gravitationally set. Feedback blows bubbles, yet the dark structure holds the larger pattern. Example in real terms, the Sloan survey mapped millions of galaxies. Its two-point curve rises steeply under 5 megaparsecs, then slopes gently. You can fit this with a power law surprisingly well. Add a small bump later and the fit becomes precise. That bump is the bow feature, a frozen early universe ring. Halo models also predict bias, massive halos cluster more than average. So rare giants amplify correlations, extending influence across larger distances. Observations match these predictions, tightening confidence in gravity's storyline. Rule of thumb, gravity likes company, and company attracts more company. So the picture is a memory lattice, preserved by steady gravity. Now for the standard ruler hidden in galaxy positions, the bow. Baryon acoustic oscillation means a spherical density ripple from primordial sound. Caring here gets practical. This ruler lets us measure cosmic expansion. In the plasma era, sound raced outward from every tiny overdensity. Gravity pulled matter inward, while pressure pushed gas and light outward. When atoms formed, pressure support vanished, freezing the outward shell in place. Dark matter stayed near the center, anchoring a two-scale pattern. Galaxies then formed with a mild preference, near both scales. The separation is about 150 megaparsecs, moving distance. That equals roughly 490 million light-years on today's yardstick. You cannot see a ring, but the statistics reveal it. pair counts show a small hump exactly at that separation. Sloan, eBOSS, and eBOSS all measured it across huge volumes. The signal is only a percent level boost, yet unmissable. Combining redshifts turns the ruler into distances and expansion rates. That gives Hubble parameters at different epochs, tightening dark energy models. It also cross-checks supernova distances, guarding against systematic mistakes. Example, in real terms, millions of pairs cluster near the bow scale. The curve's peak lands within a few megaparsecs of prediction. Surveys across hemispheres agree, despite different telescopes and selection effects. One-sentence recap: early sound waves left a ruler the universe still honors. That persistent ruler links far galaxies through a shared ancient push. Zoom into a filament, a river of dark matter and galaxies. Here, pattern means orientations line up more than random chance. It matters because spins encode how matter flowed during assembly. Tidal torque theory explains it. Neighboring masses twist, forming protogalaxies. The twist sets preferred axes long before stars fully ignite. As collapse proceeds, inflows arrive along filaments, reinforcing those directions. Mergers can flip spins, yet nearby galaxies often share alignments. Ellipticals tend to point along filaments, while spirals show nuanced trends. Low-mass spirals align with filaments, high-mass ones sometimes flip perpendicular. That mass dependence matches simulations, tying theory to observation. Surveys like SDSS and GAMA find modest but significant signals. Think 5 to 10% above random, within 20 megaparsecs. Lens shear maps also reveal correlated shapes across similar scales. Alignments weaken with distance but persist within connected structures. Gas accretion channels sustain the memory, even after minor disruptions. Example, in real terms, a filament segment hosts aligned spiral disks. Across 10 megaparsecs, many spins lean within a narrow angle. You would not notice by eye, but statistics make it plain. Bottom line, local gravity fields nudge orientations, preserving shared directions. Those nudges echo ancient tides, tying neighbors across surprising spans. The effect is gentle, yet stubborn against cosmic noise. Future deep surveys should map it sharply, across mass and time. That map will expose how filaments steer growth from dawn onward. Step back again and watch everything drift through gravitational landscapes. Pattern here means velocities point coherently over immense regions. You should care because motion biases distance estimates from redshifts. Gravity creates these bulk flows, pulling toward overdense superclusters and walls. Voids push as well, letting matter slide away from emptiness. Together they shape a velocity field, layered over the Hubble expansion. We detect flows by comparing expected redshifts with independent distance ladders. Supernovae, surface brightness, and Tully-Fisher give those independent distances. Subtract the Hubble part, and coherent motions remain as residuals. Our local group moves about 630 kilometers per second. That motion is measured relative to the microwave background's dipole. Structures like Shapley Attractor contribute far beyond our local neighborhood. A vast region dubbed the Dipole Repeller also shapes the flow. Galaxy streams trace toward Laniakea, our broader supercluster basin. Simulations reconstruct similar rivers, confirming gravity's persistent guidance. On scales of hundreds of megaparsecs, directions retain surprising coherence. Example, in real terms, peculiar velocities align across several 100 million light-years. Surveys like Cosmicflows chart arrows that cluster, not scatter randomly. Correcting for flows tightens cosmological measurements, especially growth rate constraints. It also reduces tensions between surveys by removing local motion bias. Rule of thumb: never trust a redshift without considering the river. So the picture is currents within expansion, steering far-flung galaxies together. Patterns also ride magnetic fields, stretched between merging galaxy clusters. Here, persistence means coherent fields and shocks span megaparsec scales. Caring matters because these fields guide cosmic rays and heat gas. Turbulence amplifies seed fields, while shocks order them into arcs. Relativistic electrons then glow in radio, tracing those ordered directions. Mergers slam intracluster gas, driving both shocks through the tenuous plasma. Magnetic drapes align along the shock, producing polarized radio relics. Bridges of synchrotron emissions sometimes link clusters, revealing intercluster magnetism. The famous toothbrush relic stretches over 2 megaparsecs, sharply defined. The sausage relic shows similar length, with strong polarization fractions. X-ray edges mark the same shocks, confirming multi-wavelength coherence. Simulations reproduce these arcs from converging flows along filaments. Even voids may host faint fields, hinted by blazar gamma halos. Those halos arise when cascades bend in magnetized intergalactic space. Example in real terms, a cluster pair glows with a radio bridge. Over 3 megaparsecs, polarization vectors line up along the span. The ordered geometry persists despite turbulence, revealing a robust memory. Such structures teach transport physics beyond gravitational dynamics alone. Bottom line, magnetized shocks write long, bright lines across cosmic distances. Those lines persist because flows and fields reinforce each other. Now a sanity check before our brains spot faces in clouds. Persistence here is statistical, not identical clones repeating through space. Caring is crucial because misreading patterns can mislead entire models. We quantify structure with correlation functions and power spectra, not vibes. The power spectrum tracks variance versus scale across wave numbers. Inflation predicts near-scale invariance with spectral index below 1. Planck finds about 0.965, slightly red-tilted. That number says big scales carry a bit more punch. Bow adds wiggles to the spectrum, our frozen sound signatures. Window functions blur features, depending on survey geometry and selections. Cosmic variance also bites because we only observe one sky. On the largest modes, uncertainties remain stubborn, even with great instruments. Some large-angle anomalies exist, but remain debated and method-sensitive. Robust signals survive cross-checks, instruments, hemispheres, and analysis pipelines. Good practice tests null hypotheses before claiming dramatic alignments. That discipline guards us from pareidolia, the pattern-hungry human habit. Example in real terms, bow detections clear 5 sigma across surveys. Independent reconstructions sharpen the peak, boosting significance by design. Spin alignments appear weaker, yet persist across multiple independent datasets. Flow coherence emerges from different distances and methods, agreeing broadly. One-sentence recap: real persistence passes statistics, consistency, and replication thresholds. That is how we distinguish hidden order from compelling coincidences. So yes, galaxies a billion light-years apart can share direction, not by telepathy, but by ancient ripples and persistent gravity. Light carries the earliest echoes, matter preserves the mid-game memory. Flows and fields add flourishes, sketching arcs across the dark. Across all of it, statistics keep us honest and grounded. Patterns persist because physics is steady, even while space expands. They are not copies, they are relationships that refuse to fade. That makes the cosmos feel connected, without breaking causality at all. If this clarified the hidden order, pass it to a friend. It helps more curious minds hear the same quiet rhythm. Thanks for traveling the web with me. See you out there.